Fundamentals of digital transmission. This is the second part of digital communication. Remember, we have covered the first part, which is analog to digital conversion, ADC, in the previous videos. And now we look at part 2, which is digital transmission. We look at how to transmit the signal from one place to another. The topics we'd like to cover includes the line coding, pulse shaping, and Nyquist criteria for zero ISI. And then we'd like to go over to controlled ISI, partial response signaling, where we cover binary and binary signaling with precoding, MRE baseband communication, and we look at carrier modulation, including ASK, PSK, FSK. We'll look at both binary and MRE communication. We'll also cover the I diagram. So we are ready to go. We'll start with line coding. Okay, now in baseband communication, baseband transmission, we need to represent zeros into the zeros and ones, which is the last thing we did in the conversion. We ended the PCM, pulse coded modulation, with getting ones and zeros. Now the question is, what is physically inside the cable or the fiber optics? What is really one and what's really zero? Is it voltage or current or any of them? And what is really one and what's really zero? We will start by simply assuming that we are sending pulses. So now we need to know, how do we represent the zeros and ones into pulses? This is called line coding. We look at the main line codes, main types, their performance criteria. We look at the a bit advanced example. I just share the example of the HDBN. And then also we need to look at this power spectral density. So basically we look at line codes and how we compare them. The following figure shows you different possibilities for representing ones and zeros. Can we go up and then positive and then negative, or should we go positive for ones and then zero for zero? And what is really the best way of doing it? And this is what we're going to do next. So these are just examples of line codes, which will be explained in more details. Okay, so we can say now line codes are electrical waveforms for the purpose of transmission over the channel, electrical or optical if you like. Okay, the first line code is called on, off, or unipolar, and the name is clear. Unipolar because it's only one polarity, and on, off, we turn the voltage on. So we have, for example, 5 volt. It could be another value. The exact voltage level will determine the power. But here we're saying we have 0, 1, 0, 1, 1, 1, what have you. Then we have representing 0 with no voltage, representing 1 with positive voltage. Okay, that's as simple as that. This is called on, off. Off for 0, on for 1. It's also called unipolar because there is only one polarity for the voltage. This is a non-return to 0 type of line coding, and this is going to be clear when we show the return to 0 for comparison. Those dotted lines represent the bit duration. So this is the time allocated for 0, the time allocated for 1, and so on. There is another type which is called on-off return to 0. Why do we call this return to 0? Because when you change your voltage level to high or low, you return to the 0 voltage within the bit duration. If you compare these two, this is the bit duration. The upper one, we have a constant value high level voltage, and we are not returning to 0. For the lower one, we are returning to 0 within the bit duration. So the time is divided like into 2 parts, one high voltage and the other one is returning to 0. Why did we go from here to here? Now, if you have long sequence of zeros, long sequence of ones, like in this case, I'm just showing 3, but if your data rate is 1 megabit per second, it means you have 1 million bits in 1 second, and if they are all ones, you will have a continuous line, and it's very hard to divide the bits because we'll have always time jitter and synchronization issues. So we would love to have transitions in the code. So if you notice here, we are just constant at 1, while here there are marks which allow you to know where is the start and the end of the bit. So comparing the first to the second one is better in terms of synchronization, of course at the cost of extra bandwidth. You expect to have more bandwidth here because time and frequency are inversely related. If you make the pulse duration less, the spectrum will have wider coverage, which means we're going to require more bandwidth. So this is on-off, and the comparison in terms of synchronization and bandwidth requirement. Now the second type, we take it one step further. We call this the polar line code. And clearly here, it's polar compared with unipolar, because we are going for 0 we are sending -5, and then for ones we are sending +5. Again, the exact value of voltage depends on the power dissipation and other details. If you compare the upper with the lower curve, you can see here that we have returned to 0. Whether you go positive or negative within the bit duration. For example, here we send, let me just show this another color here. We are sending, for 0 we are sending -5, while for the second scenario we have sent -5, but we return to 0 within the bit duration. Similarly for the one we sent +5 and we return to 0. So this is other two types, polar, return to 0, and non-return to 0. So the basic disadvantage of this code, first, why did we go to polar? Okay, for the unipolar, if we have long sequence of ones, we have solved this by going back to 0, return to 0, to avoid the long sequence. But if we have long sequence of zeros, there is nothing to do about it. So the unipolar had a problem with long sequence of zeros. And this is why we introduced the polar case. In the polar case, if you focus here on the second code, you notice that there is always transitions between bits, so you will not get a constant value that you have to worry about what is the start and what is the end of the bit. So this is perfect for synchronization. But the problem with polar, whether the first or the second, whether return to 0 or not, it requires multiple voltage sources, because you need to regenerate 5 and -5. In principle, we have 3 possible levels for the voltage here, and there are 2 different polarities for the voltage here. This is the polar, and the 2 subsections, or the 2 types, which are non-return to 0 and return to 0, why we introduced them and their advantage and disadvantage. Okay, of course, in terms of bandwidth, the second one, of course, requires more bandwidth because the pulse width is smaller. Now, we want to do better than this. So we introduce the bipolar or pi-phase codes. In the bipolar case, what we do, we don't want to avoid the bandwidth requirement. So the way it works, we are sending 0 and then +1, and for 1 we are alternating, okay, because we call it bipolar, 2 polarity, because for the same signal, for the same one, we are sending 1 time positive, 1 time negative. So see, for the 0 we're keeping everything 0. For the 1 we send +1 and then -1, +1 and then -1. Zeros remain 0. This is going to solve the problem of long sequence of ones without increasing the bandwidth. However, the problem of long sequence of zeros is not solved, because long sequence of zeros, there is no transition. Okay, so to solve this, we can use the Manchester code, and the Manchester code is also called the biphase. So there are 2 names for this. It's perfect for synchronization. We're going always to have transitions. How does it work? Are we sending positive or negative for zeros and ones? Okay, we're sending low to high if we want to represent 0, and then high to low if we want to represent 0. So the information, the bit, is not in the level, but rather in the transition. Going within the bit duration from low then high means we are sending 0, or high then low means we are sending 0. For example, high, low, transition in the middle. You can see the arrows here representing the transition in the middle, not in the edges. Okay, so high to low, high to low, high to low means we have 1, 1, and then 1. This is called Manchester and biphase. This is perfect for synchronization because there is always transition within any bit duration. Okay, and it has two levels only of voltage. You could have -5, +5, or even 0 and 5. It depends on what you have. But here the data is represented in the change. Are we going from low to high or high to low? The bandwidth here is a function of the sequence. You can see here that if you have long sequence of ones or zeros, there's always going to be transition. If you have 0, 1, 0, 1, then you have the pulse looks wider, and the bandwidth requirement is going to be less. But we look at the worst case, or we look at the average behavior. Now, we have seen about 6 types. We have seen on-off, return to 0, non-return to 0. We have seen polar, bipolar. We have seen polar, return to 0, non-return to 0, then bipolar, and then biphase. So what is the performance criteria that we need to consider? Which one do we choose? Usually there is a trade-off. You get something and you pay the price in terms of something else. So what did we get and what is the price? Okay, the first thing, when we compare different line codes, we prefer to have 0 DC value. 0 DC value means the average equal to 0. Like for example, if we are sending polar, where we have -5, +5, okay, that's expected to have average of 0. Sorry, -5, then +5. Other type of line codes, if you're starting from 0 and then positive, then you don't expect the average to be 0. Why do we prefer 0 DC? Because in the transmission media, cables or so, there is unintentional capacitance. This capacitance, as you know, block DC and block low frequency content. So always in communication, we prefer in general that we have 0 DC. So line codes with 0 DC are preferred. I mean 0 DC, of course, the average value. The second thing, would love to have inherent bit synchronization, which means the code is rich of transmission or transitions. A code like the on-off is not very good because long sequence of ones or long sequence of zeros, we don't know exactly what is the transition. Is this a bit? Is it here or here? Okay, it's not as easy. We need synchronization clocks, and those could go wrong. Now, under that, we have a code called transparency. We have a criteria called transparency. So when do we say that a code is transparent? A line code in which the bit pattern does not affect the accuracy of timing, information is said to be transparent. So if there is always transitions, irrespective of being zeros and ones, we call it transparent code. Okay, like for example, the polar return to 0. It's transparent because the timing information is not affected by being zeros or ones. However, in code like, for example, in a return to 0 polar, unipolar, it's not transparent because long sequence of ones have lots of transitions, but long sequence of zeros has no transitions. So transparency, the timing information should not depend on the data, zeros or ones. You can read more about this, you can search more about transparency. Alright, so what is the average transmitted power? When we compare different line codes, we have to check which one consumes more power. But this is tricky because when we look at the power, we have to make sure that they have the same performance. For example, it's not fair to say that 0 and 5, okay, you cannot say that this is going to use less power than the code of +5 and -5. Because their error performance, their noise immunity is different. Either we fix the power and we compare the line codes in terms of noise immunity, or we fix the bit error rate or probability of error, and then we compare the power. Maybe we'll look at more examples as we go on. So, but just we have to make sure that the power is reduced for a given probability of error, for a given bit error rate. The spectral efficiency, the bandwidth, of course we require the line code to use less bandwidth, and this is inversely related to the pulse width. So this is why usually return to zero scenarios, if you return to zero, you expect to require more bandwidth as compared to the non-return to zero, because the pulse width is less and the bandwidth is more. The error detection and correction capability. Some line codes, like the code which is the bipolar. The bipolar example, if you recall, send plus for +5 for 1. Next time it sends -5, and then it's +5, -5. For 0, we are sending 0. This code has the ability of detecting errors, because there is no way on earth you can get two positive sequences, two positive voltages or two negative voltages as after each other, because by definition the polarity should alternate for ones. So we call this code has an ability to detect errors. Of course, it's an advantage. Now, there are other codes which have the ability not just to detect, to know that there is error, they also can correct the error. For example, we'll take a simple example. Let's say if we're sending 0, we're sending 3 pulses. And if we're sending 1, for example, we're sending negative pulses, just for example. So what if, for a reason or other, we lost one of these and it was recognized as negative? We're going to use majority because we're sending 3. So we can still correct the error in the middle. And this is shown here on the side. Okay. For example, if somebody is sending zeros for 1, zeros and 1 for 1s, this is called the binary repetition code, because you are repeating yourself. Okay. So in that case, although one of them turns out to be an error, we can still recover the data. Okay, we can still, this is the symbol to be transmitted. This is the transmitted sequence, and this is the received sequence. And this is how we recover the data, because one error can be corrected, because we have 3, we're sending it 3 times. So making one mistake is no problem. Now, of course, one of the important things is the hardware complexity, because we have seen that some line codes require more than one voltage source. This is one example of complexity. Now, another important thing is the insensitivity to signal inversion. What if we flip the wires? What if the signal gets inverted? Are we going to lose the data? Are we going to decode the data in a wrong way? One of the examples of the line codes that is unaffected by flipping the wires or the signal inversion is what we call the bipolar line code, because bipolar send plus and minus for ones. So even if you flip the signal, you get still ones at the right position and zeros at the right position. So an example for this is a bipolar. The bipolar is one example where we have insensitivity to signal inversion. So these are the criteria: 0 DSI, inherent bit synchronization, average transmitted power, spectral efficiency, error detection, hardware complexity, and signal inversion, insensitivity to signal inversion. So I will move and we'll see some examples about the issue of transmitted power. Alright, here is a nice example. It says compare on-off and polar signaling or line codes. The upper figure shows an example of the on-off signaling, and then we have here the polar line code. The first thing we look at in terms of DC, this one has got DC, right? Because it changes from 0 to positive. So the average value is expected to be 2.5. While for the second case, if the number of ones and zeros are equal, which is usually assumed, we get average of 0. So for 0 DC, polar is better. Now, when it comes to the bandwidth, both of them are comparable because you can see the pulse width is the same. The amplitude change will not change the bandwidth. So they have comparable bandwidth. Now, in terms of power, which ones consumes more? If you notice here, I changed this to 2.5 and minus 2.5. Usually you have plus 5 and minus 5. The reason is, if we want to compare in terms of power, we have to make sure that the probability of error is the same. The bit error rate is the same. So the probability of error, the bit error rate, is proportional to the difference between the two levels. So here we have a spacing of 5, And to make the spacing here is 5, I have made this 2.5 and this is minus 2.5. So we have a total of 5 volts. Those are comparable in terms of performance. Now we can check which ones consumes more power. We'll assume that half of the bit are zeros and half of them are ones. So the power of 1 and the power of 0, we take their average. So here, for example, we get for the on-off 5 squared plus 0 squared. The power of 1 and the power of 0, and you divide by 2, you get 12.5. For the case of the polar, we always have a DC value within the bit. So we have either 2.5 squared or minus 2.5 squared, divide by 2, you get 6.25, 6.25, which says, or which means that the polar requires much less power. It requires, in fact, half the power for the same performance. Of course, there are other trade-offs, including the number of voltage supplies or so. But remember, the power is related to the square, so it's better to be close to 0. So we conclude that for the same difference between the two levels, polar consumes half the power of the on-off scheme. You can prove this as an exercise. Try to fix the power and see how much is the spacing between the two. You'll find here that you have more spacing. Okay, so if you fix the power, then you work backwards. You make this an unknown, A and A. So you make this equal to 12.5. You solve for A, and you find how much is the required, how much would be the spacing if the power was the same. Okay, bit synchronization, they are the same, they are comparable. Both are poor because there is no transmission, there is no transitions. A long sequence of ones or zeros would mean lots of troubles. Both have no error detection or correction capability, and both require 2 voltage supplies. Okay, oh sorry, polar, this one requires 2 voltage supply, this one does not require. This is a basic comparison between the two. You can exercise yourself by trying different line codes. Apply the same example for different line codes. Okay, here's an example of advanced example of line coding, high density bipolar. This is not an easy example, but understanding this is going to make sure that you really understand what's going on. Okay, so you can find this. You can find a similar example in the text of Lathy for communication, or you can read about high density polar. You can even freeze the video and try to understand what's going on here. Because we're just giving the basics. What you see in real life could be another example. So this is called HDBN. It basically alternates between, it's a bipolar example where you have positive and negative. To avoid long sequence of zeros, we are using some violations. So violations means we are violating the sequence. We should have negative and then positive. We have violations, and then we're supposed also to have some other details. When do we violate, and why and so on. This is, I leave for you to read. It's a more complicated example, but as I said, understanding this will guarantee you understand the remaining part of the codes. Okay. Next, I'd like to make sure that we discuss the spectrum. We usually divide the impact of spectrum into 2 parts. So the data will come here. The pulse shaping filter will define the shape. Is it going to be squared or impulses or other shape? We'll see later on. And then we get the spectrum. So the spectrum does not only depend on the line code, depend on what kind of pulse shape do we use. Is it square or not? We're going to look at this in more details. So the output spectrum depends on the pulse shape and the arrangement of the data. So here we have the pulse shape is chosen just a square for simplicity. Here is the data being positive or negative, and this is the result. The resultant spectrum, spectrum of this time signal depends on the 2 things, not just the pulse, not just the sequence, but the pulse shape also. This is determined by the line code. Are we going positive or negative? Are we just going positive? These are the transitions, and the pulse shape will have an impact. The transition is determined by the line code. Without going into deep into the math, we are going to just look at comparison here. Remember that usually the ones that have DC this is the spectrum. This is the normalized spectrum, where we see the pore density or the spectrum distribution as function of f times t. We see that, okay, some channels with infinite bandwidth are required to transmit any of these line codes because there is going to be tail, but usually we are looking at the relative performance. So on-off as DC requires less bandwidth. As we go to bipolar, okay, you can think of this as a bandwidth. Okay, well, here it goes into higher frequencies for the bipolar. Also for the Manchester, which is the one that's also used in the Ethernet, by the way, the Manchester or biphase, it's widely used. You can see that the bandwidth requirement increases. So we can say that power spectral density of the line code, we're not going into the derivation, okay, we're just showing the relative performance. The reason for not being able to use Fourier transform here for finding the spectrum, because we have randomness here, and the randomness come from the data. Data could be positive or negative. We know that for a square pulse we get sync in the spectrum, but it's more than just the sync. We have the information itself that determines what the spectrum is. So this requires into a little bit of stochastic and looking at power spectral density, which is beyond the scope of our presentation today. We just need to know that Manchester requires more higher frequencies than bipolar, and bipolar requires more bandwidth compared with on-off. So they are not all the same. Here's an exercise for you to practice, and please write your answers or comments down under the video. Consider the following sequence of ones and zeros: 1 0 1 1 0 0 0 1. Sketch the waveform. This could be one word, waveform, using the following methods of representation: symbols, ones and zeros, line coding. The first one is use on-off. Just sketch the waveform that's going to represent this data, none return to zero. Also, I'd like you to sketch the Manchester code for the same example, where a high-low transition represent 1 and a low to high represent 0. Which of the line codes has 0 DC? Which one of the two line codes require minimum bandwidth? So please write your answers down, or share your answers, at least for the second part, in the comments. Thank you. This is it about line codes.